Okay, so I'll start recording because we're basically here, ready to go. Oh, and Daniel, I didn't see how you were. How are you? Good. Glad to see you're doing good. I have been well. I have been well. I've been doing just kind of my own research. I have a paper to finish writing it. It's due September 3rd or something like this. It's very reasonable to get done in that time.
Okay.
It's in the research. This paper is applying kind of like complex network embeddings, which is more like a data sciencey thing, to trying to find money laundering in transaction networks. So we're trying to find suspicious transactions. We don't have any ground truth, but we're trying to develop some technique that would flag certain transactions in this large network as being suspicious of money laundering. And so we are using Node2Vec embeddings. I don't know if you know about some data science things. Yeah, right. So
That sounds interesting.
yeah, exactly. So we're trying to see if we can identify some sort of like organization between the nodes. Not that they're organizing to be central, but that they're actually organizing to kind of evade centrality, right? That they're trying to that there's some intelligence in the way that they're doing the transactions that shows that they're actually trying to avoid detection, and that would be very suspicious in a transaction network. So blah blah blah. At the end of the day, all that really means is I run some Python scripts, I get some pretty pictures, and then I put it on I put it on a paper and call it a day. So it's more science, yeah, more science.
I'm half computer science, half data science.
Uh-huh.
Turning into a mathematician.
Yeah,
So
yeah.
yeah.
I get it, right. So you have a similar feeling. Absolutely. I see that, right? Yeah. So anyways, yeah, there's a in New York in December, there's a conference on complex networks. So we're going to submit a paper to that and hopefully it gets accepted. I go present it there. So that would be good. But anyways, okay. I realized I recorded it. Anyways, I'll just keep that on recording if people are interested in what research I do. So we are here. We are here. Undergraduate analysis. Understanding analysis, number 5. So let me open up the textbook. As I stated before, I don't need that. That's okay. Here we are. So as I stated before, we are going to be focusing on 2.7 and 2.8, but I'll do a quick review of what we've talked about so far in chapter 2, just to kind of get started here. So the main purpose of the beginning of this chapter, maybe I'll look at the table of contents instead of scrolling through here, right? So the main purpose of the beginning, the first 3 subsections or sections, I guess, are just to identify what a sequence is and limits and just basic properties about limits and some things that we will use lots of other times. And then we go into some of these other characterizations of completeness, right? And it'd be nice to show kind of all the logical equivalences between all these things, but vaguely with some asterisks on it. The monotone convergence theorem, the Bolzano-Weierstrass theorem, the Cauchy criterion, the what am I trying to say? The axiom of completeness are all kind of characterizations of completeness, right? And the nested interval property, which is somewhere in here, those are all kind of characterizations of completeness, vaguely equivalent, but with some weirdness happening because of Archimedean principle and all that, but whatever. So that's kind of the establishing part here. And then, we a little bit take a look at infinite series, which is a very, very real analysis kind of thing to deal with. But then we also have a whole section on properties of infinite series. And then this last section is kind of just like doubling down on that specific detail. So infinite series, double summations, which, to be clear, right, is very related to an exercise we did. I think it was at the end of 2.2. Let me see here, right? At the end of 2.2. No, maybe it was at the end of 2.3. Where is it? Yeah, this guy, right? We talked about iterated limits. And so this was kind of a little bit complicated. And this was like the limit, a double limit in a sense, right? And so we're not going to be using exactly these details, but a similar kind of thinking in double summations, where we talk a little bit about what it means to sum across a doubly indexed array, and there's actually a way to just write that as a single limit, a single variable limit. So blah blah blah. Okay. So that's kind of our little 1-2 of what's going on. So let's just go through some of these properties and maybe we can try some exercises. I think I chose a couple, but I haven't actually really looked at the really tried them. So we can maybe try together, and then I'll have these open, not open, but just ready at the ready in case we got run into some problems. Um, and yeah, okay. So let's get into it, and maybe I'll start by just asking for the people who are here, the two people who are here. How did you guys read through this? I think Daniel, you mentioned to me a while ago, 2.8 was kind of giving you trouble, which we'll hopefully talk a little bit about today. But for both of you, I don't know what's the impression of 2.7, 2.8. Interesting, boring.
It was cool. Perhaps something that I noticed was that so here you have a bunch of different tests for convergence, right?
Yes.
Um, and you know, it's sort of like a pool of different tests, right? And you get to derive all of them, but perhaps
Right.
as you go deriving them, you will make an emphasis that it is a tool that you can use, and then perhaps when you're solving another problem, you don't think of that tool just because you were just solving, proving some theorem as an
Mm-hmm.
exercise rather
Mm-hmm.
than like that's what I noticed.
So you feel like it comes up like the tests, like as part of the exercises, come up in later exercises. You're saying?
Yeah, I think yeah, I think that is one of them. I don't remember now.
Sure.
I think
Okay.
the absolute convergence test appears a lot too. And
Yes.
now it's which other one?
I think yeah. Well, we'll see. We'll go through, right? Yeah.
Yeah,
Here.
yeah.
We'll go. So we have these tests. Comparison test, maybe. I guess is the other one that
No,
could.
no, it was a test that so if it converges if it converges absolutely, then it converges.
Then it converges, right?
Like, I mean, yeah, I forgot the words now, but yeah, like if you take the absolute value and it converges, then without the absolute value, it also converges.
Yes. Right. Where is that? That is somewhere in the exercises here, right?
I don't remember now. Like it's called the absolute convergence test.
Uh, you're right.
Maybe.
Here is this it?
Oh,
If an then well, it's a definition I know, but if an converges, then we say that the original series converges absolutely. Yeah, I guess that could be a theorem.
yeah, we do have a theorem that absolute convergence implies conditional convergence. Like after that page, probably. So the next page should be, I guess.
I get it, right? Alternating series test explored, and actually no, right? Which is I know what you mean.
Theorem 2.7.
Well, then this is saying that any rearrangement of the original, including the including the null rearrangement, right? Including the do nothing, right?
Yeah.
Yeah. Okay, then that is it. Yes, right. That is what you're saying. Oh, right. So yeah, so that'll be that is thing. And I was thinking we do this proof, that's actually pretty much the only proof that I wanted to do from the thing. I mean, it's kind of I'm maybe slightly fuzzy of what's going on at the end here. I think I understand it, but maybe we can iron out some details about what's going on at the end here. But and then maybe we can try. I was thinking like some intuition kind of proofs like this or something like this. I mean, not proofs, but just problems like this. And then I was thinking doing the ratio test might be fun because the ratio test I remember that being one of my favorites from when I was taking Calc 2. I guess this is 5 years ago or something like this. I remember ratio test being a very useful one. So anyways, so that's that might be fun to prove. Okay, so let me just kind of take a piece by piece here, right? So we're talking infinite series. So the first very important thing is to remember that an infinite series is this kind of like summation of infinite terms in the sequence, and the point is that we say that the infinite series equals some real value, meaning the limit of the partial sums is that real value. And that's our definition. That's our defining feature of what an infinite series converging is, right? So we say that the infinite series converges if it is equal to, if its partial sums converge and it diverges otherwise. And so it's really a notational thing, right? Like this is not it's a notational thing essentially, right? Which just directly means this, that the limit of the partial sums is that. But there is some algebra we can apply as well. So that's the first thing, right? Algebraic limit theorem for series, right? Is to say that, it respects kind of addition and multiplication. scalar multiplication essentially. And so that's just useful, and that basically comes right from the fact that we're really behind the scenes dealing with the limit of a sequence, and we already have a algebraic limit theorem for sequences there. So I don't think we have to really talk about that. Then we have this is pretty relevant. So maybe we can talk about this for a second, right? So Cauchy criterion for series. We have an alternative way of defining the convergence of an infinite series in terms of the partial sums not being convergent but being Cauchy, which we know is equivalent, right? Cauchy sequences are the convergent sequences for R, and so then we can just kind of rephrase it as to say that the partial sums must be Cauchy, and so the partial sums being Cauchy means that Sn minus Sm, which is the partial sum up to n minus partial sum up to m, for these kind of, we can add a little extra condition here that we need one to be strictly bigger than the other. Then we have that it's less than epsilon. This value is less than epsilon, which means that the sequence is Cauchy. The partial sums is Cauchy, which means it's convergent. And so clearly we have that the original series also converges. And to be clear, we're not saying that it's equal to any particular limit, right? There's not a particular sum. It's just that it does converge. Okay, and then this gives us, as it says, economical proofs of several basic facts. So this, I would say, is the divergence theorem. Maybe I would say the contrapositive of this, which is that if this limit is not zero, if the sequence that you're summing does not tend to zero, then the series must diverge. And then we have the comparison tests, which are, I think, fairly intuitive. If the big one converges, then the one that's smaller than it must be squeezed in to also converge. And if the smaller one diverges, then the bigger one must also diverge because it's bigger. It's just kind of my intuitive explanation, but of course you can put some more rigor to it by just kind of doing these things. But we can kind of collect our tests here, right? So our tests for convergence are Cauchy criterion, which is not particularly useful on its own, but gives us really nice series like results like this. So this is like our divergence test. This is our comparison test. And then blah blah blah. Some things about geometric series, but then we have the absolute convergence test. So this is important, right? So if the series, here we have, right? So if the series, the absolute value of all the values in the sequence, the series of that converges, then the original one also converges. Not necessarily to the same limit, but it does converge as well. But we will see that it will converge to the same limit. Will it converge to the same limit? Yeah, it should converge to the same limit, right? Because that's what this final thing is saying. Anyways, we'll get there. So that's the absolute convergence test. And then the alternating series test is saying that if I have a decreasing sequence, strictly decreasing, and tending to zero, or not strictly decreasing, decreasing, and tending to zero, then the alternating sequence, the series of that, where I'm alternating negatives, positives, and things like this, will also converge. Okay, but not necessarily to anything in particular, and we can maybe the proof is not here. It says an exercise. We could do that, but maybe just for time, we could do it. I don't mind doing it, but that one I did actually. I did this one in preparation for this. But anyways, whatever. Then we're almost there because the main thing I want to talk about in this section is the rearrangement. So we'll do that. But this is a key thing, right? So if the absolute value series converges, then we say that the original series converges absolutely. But if the original series converges, but the absolute values don't, then we say that it converges conditionally. Okay, so this is a key piece of information. So like a definition. So I'll put it right here. So that's good. And I'll also just click something here for the recording. Hopefully that's good. Okay, so now with that in mind, we can start talking about rearrangements, right? So I think rearrangements are very interesting. So rearrangements are where you take the series, but you put it in a different order. And does that do anything, right? Because in the finite case, clearly doesn't, right? Clearly doesn't do anything. But in the infinite case, it sometimes does. So this is the thing, and this is where the distinction about talking about absolute convergence and conditional convergence is relevant. So let's do this, right? So the first thing is, what is a rearrangement? I think it's fairly clear what the word rearrangement means, right? You just kind of put them in a different order. But what we really mean, you can kind of like identify. You could draw arrows, right? So, well, this is not a rearrangement, but yeah, this is not a rearrangement. But so like if I just have I don't want to bore anybody, but let's just say, if my sequence is 1 plus 2 plus 3 plus 4 plus ... and I instead go, 2 plus 1 plus 4 plus 3 plus ... then you can see that we have like, we've kind of shifted things here, right? And we can draw a bijection from these elements to these elements in a order, right? In an ordered kind of way. And so that is our definition of a rearrangement. So we have that it's two series are rearrangements of one another if there is a bijection such that the f of k index of B is ak. So the f of 1 index, this is B f of 1 is going to be a1. Like that. So f of 1 would be 2 in this case. So 1 is what was originally at 1 is going to be at index 2. So I don't want to, harp on the point too much if it's clear, but that's the, that's the definition, and it comes up in this proof right there, right where we talk about the actual bijection. But anyways, and then this is the main tool from this section here, which is that if a series converges absolutely, then any rearrangement of this series converges to the same line. And so we'll start today by going through this proof here. We'll do it together. Now, sorry, I have to open up my own notes because I did do this ahead of time. Again, the end maybe I'm a little shaky on, but let me just get my own notes up here. And this is here. Where am I? I'm too far. Okay. Okay, if everybody's ready, I will begin. I'll just make sure that everything's recording properly and you can see. Okay. So this is, maybe I'll just copy it from my notes here. So if we have a series that converges absolutely, then any rearrangement converges to the same limit. And so let's remember what converging absolutely means. It converges absolutely if the absolute value of the sequence converges. Of the series, I guess. No, sorry. The series of the absolute values of the sequence converges is what I'm trying to say. It's a lot of words, but just like highlighting this, I think does say it, right? So that's that. And it will converge to the same limit. Okay, so let's go into it here. Of course, I'll follow the proof in the book, but maybe I'll try to write it out nicer, or how I want to write it out, right? So the first thing, we have a couple things that we have to actually use, right? So we need to like have some notation here, right? So if we have the sum, let's just say the sum ak, I'll just use that notation to mean all of it, right? From 1 to infinity, converges let's just say, you know, yeah. So I guess how should we say? I guess it is a result that we haven't actually shown, but if an converges, the absolute values converge, then the original an also converges. Like that, we haven't shown that, which is kind of curious.
Wait, is that true? Like I could have numbers that alternate between 1 and -1, and the absolute value is a constant, so it converges. Or do you mean the sum of the sum of the?
I guess I mean the series, right? So I mean like if
Okay.
if this converges, let's say if this equals a, then does this imply that this also equals a? So it's, you know, question.
Well, definitely it converges. I'm not sure if it's trivial that the other series, the conditional one actually converges to the same value.
Yeah, right. Because the we do have the the test here, right? The not the alternating, but if this converges, then the other one converges as well. But yeah, you're right. We don't have it to the same limit, right? So absolutely, it's like the absolute convergence test. So it does converge, but not to the same limit. But I feel like we use that here. We do use that it converges to the same limit.
I'm not sure. I think it's actually part of the proof. I think they prove that it converges to the same limit in the rearrangement.
Okay, so let's just proceed, kind of, right? So let's just say this, converges absolutely, right? Let's say this, is a rearrangement of AK, of AK. And so, this means that we have some, f from n to n such that, b of f of k equals ak, for all k greater than or equal to 1. Also, f is bijection. Okay, so then we need we need the partial sums, right? So we'll just have some notation here, right? So we'll say that we'll let Sm be the sum, I goes from 1 to m of I guess. And then we'll let Tm be the sum I goes from 1 to m of bi. And so we need to show that they converge. Well, let me look at the way that's actually written here, because I think I just have the same as my notes. But immediately it says this converges absolutely to A. So I don't, and I think that means this converges to A, right? Like this, it converges absolutely, but it also converges to A. I guess we don't technically know that the absolute value of the series converges also to A, but we do know that this series converges to A, which I think should be fine.
I see your point now.
Like, we don't know that the series of the absolute values also converges to this A. That's my point, right?
Yeah. But wait, it says converges absolute. What is the definition of converging?
Yeah, right. Like, I don't think we have a nice definition of. We say that this converges absolutely, but we don't have it never defined what it means for it to converge absolutely to something, because that could either mean two things, right?
Yeah.
It could mean like either it converges to, so if we say this converges absolutely to A, that means that this series converges to A, or we mean that the absolute value of this series converges to A, or we mean both, but then that might be that's like a lemma that they both converge to the same thing, right?
Right. Yeah.
So that's I will, but we use the fact here that this says thus we want to show that TM converges, like this partial sums converge to A. So that means that these partial sums must converge to A, which means that this must converge to A.
Right. So perhaps the definition of converging absolutely to A does not really right. I mean, like on the definition above, right? That does not really
Mm-hmm.
tell anything about the absolute convergence to be A. I guess that now.
Right. So let's
Yeah.
maybe like just like, right, this is the definition I'll work with, right? So I'll say that, the series AK converges absolutely to A, and this means the series AK equals A, so it's equal to partial sums, blah, 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 and the series, the absolute value of AK converges. These two things, but not necessarily to A. I don't know if we need that, but so that's kind of how I'm interpreting it. It might be that they are. It might be that it's the same thing, but I don't know. We haven't shown that, so. But I think that's maybe all we need, right? Okay, so with that in mind, let's so we know that SM. So let's say 2A. So that means that SM here, this converges to A like that. So we need to show that TM converges to A. This was TM's a rearrangement. We need to show it converges to the same place, to the same thing. Okay, so we need to start using a bunch of our facts that we have here to get some bounds on this, right? Because at the end of the day, we want to be able to bound TM minus A, right? And so we need to find somewhere where we can, do some epsilon business to split it, right? Because like the point of showing this limit is we need to bound TM minus A with something. So let's just start, collecting some facts that we can use here. So the first thing that we can do is we know SM, and we'll call it SN, whatever, converges to A. So that means that for all epsilon greater than 0, there exists an N1, in N, such that N Sn minus A is less than, epsilon for all N greater than or equal to N1. But, for reasons you'll see later, we'll put epsilon over 2 here. I mean, you can, so put, whenever you have an epsilon over 2 like this, just, if you were actually figuring this out on your own, you just put an epsilon, and then you realize at the end you need an epsilon over 2, and then you just come back and put epsilon over 2. I mean, it doesn't matter, because it's any epsilon greater than 0, and you can just kind of fit it here. Okay, so we have that. So we can bound this value, Sn minus A, for all n that are bigger than this n1. Okay, so maybe if we can kind of like split the difference, remember again, we're trying to like find this, Tm minus A. So the distance from Tm to A, but if we can find the distance from Tm to something, and then from that something to A, and if that something is bigger, is further along in the sequence than n1, then we know that this distance is less than epsilon over 2. Then we just have to figure out what that something is in a way that makes this side make sense, that we can kind of find the distance here to be less. Okay, this is kind of some logic. We know the sum absolute value AK converges. Okay. Well, Cauchy criterion, and so this is actually I think this is a correct definition, because we just need to know the fact that it converges. We don't need to know what it converges to. We just need to know the fact that it converges, which by the Cauchy criterion tells us that, well, the Cauchy criterion says that for all epsilon greater than 0, there exists an N2 in N such that, and I'll just put it here, for all N greater than M greater than or equal to N2, we have, okay, and we have what? So the Cauchy criterion tells, if I go back up, I didn't put it, so let me bring it here. It's right here, right? So that this expression is less than epsilon. A m plus 1, m plus 2, all the way to a. So it's a m plus 1 plus a m plus 2 plus ... plus a n is less than epsilon. Okay, so but let's just okay, it was less than epsilon, whatever, right? I guess I guess I mean the absolute values of all this, right? Because it's the absolute value sequence there, right? So it's all the terms are in absolute values, and that this is less than epsilon. And so, but the outer absolute values don't really matter. So we know that the sum k goes from m plus 1 to n, and we know that m plus 1 is at least n, right? It couldn't be less than n.
At most n.
At most n, but it's going from.
I mean, n plus 1 is at most n. Otherwise, the sum is not defined.
Yeah. Right. Yeah. So then this is from the absolute value of AK, right? Is less than epsilon, like that, right? So we have this kind of fact, and I'll just kind of put it as a star here. Maybe this will be our. I'll just call it, well, I already did that. So call it like star 1, call this star 2. And again, this is for all epsilon. So if I just choose n to be the bigger one, right? Then for all, n greater than or equal to n, right? Well, for all epsilon greater than 0, and for all n greater than or equal to n, this n which is the bigger of the two, then we know two things. We know that Sn minus a is less than epsilon over 2, and the sum k goes from m plus 1. I guess I mean, I guess here I have to put n like that, right? M plus 1 to n of the absolute value of AK is less than, and we'll also put an epsilon over 2 here for that. Okay, so whatever. So we have these two facts. So this is kind of like I just kind of grouped together star 1, star 2 into star 3. That's all it is. Right? I'm not using anything here. I'm just kind of summarizing our facts. We have this property. Okay, so we know that that's helpful. So as long as we're past that point in the sequence, then we have these are very small, and that's half of what we want here. So maybe we need to pick some kind of Sn here that makes this work. So this is kind of where we move on to the rearrangement, right? So BK is a rearrangement. Oh, if I can spell, that's important. Meant of a of a n. Let's just say. Okay. So notably, the first capital N terms in the sequence, right, don't have these properties, right? But once we're past this, we have all that, right? So that means that a a1, a2, ... an, this set must appear in BK somewhere. Could be rearranged, blah 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 blah, right? So what we're gonna do, and remember that to know, like, a, let's say a2 or a1 equals b what? Well, we have a function for that. We have f of k. It's f of k, right? We have this f of k. F of k. So what seems relevant is the furthest that any of these get put into the sequence. Because if we know where the furthest one is, then all of them will be before it, right? I mean, obviously, that's the definition of furthest. So we will maybe use that, right? So let me just read what I have written here. They must all appear in the rearrangement. We want to move far enough into this series. Well, this I didn't, well, I guess that's what I mean, right? This series, so that all these finite terms appear. Recall we have a bijection between the indices. Thus, yeah. So we just pick M to be, right, the furthest. So FK, sorry, to be the maximum of, well, f of 1, f of 2, ... f of n, right? The furthest that any of these get mapped into. So that means, right, that as long as we are at index, right? So that's, as long as, how should I write this? So if m greater than equal to m, then the sum Tm, right, the sum of the first m terms will be Sn, capital N, the sum of these first capital N terms, plus, and I'll just say like extra, right? Whatever was left over. There might be more things kind of fiddled in there, right? So it's like a capital N, let's say capital N was 10 or something, then this could be mapped to the 20th spot, and then there's there's all the stuff in between that's extra. And there's some extra there. But the point is that this extra will be finite, right? Because it's a finite sum up to m here, right? And then we have this kind of extra bit like that. Okay, so this is where I get a little fuzzy on what's going on here. So let's see if I can kind of word it together here nicely, based on what's said in the book. But anyway, so the point is, so far as we've used that it's the original series, the series itself converges to A. It absolutely converges. We don't know to A, whatever. Like, we don't know that the absolute value series converges, but we don't know what it converges to, but we know that it converges. So we can bound this value, right? And then we can, and that's as long as this n is big enough, right? As long as our value is bigger than this n here. And then we know the index of the furthest point from this finite sum, right? The first capital N terms here. We know how far we have to go into the rearrangement before we get all of them, so that the rearrangement here is Sn, the first capital N terms, plus some extra. So now we're trying to bound Tm minus A, right? That's what we're trying to give a bound to. Well, this is just equal to Tm minus Sn plus Sn minus A, which triangle inequality we know is less than Tm minus Sn plus Sn minus A. Okay, so what do we know? We know that m, right? M is greater than or equal to m. M like this. There you go. That's what we know.
Yeah, so I guess the point is that the first term on this sum is that extra stuff, and so what happens with the extra, right? Well, I guess that the point is subtle and it's not very clear on the book.
Mm-hmm.
But what they're saying is that let's see. So you have that for, like, I forgot now what number you were using. I think it was n1. Yeah, you have that for things beyond n1. right? For any small n beyond n1, the summation.
Okay, n2. Yeah.
Sorry, yeah, you have this convergence, like this inequality, right? Like as n minus a is less than.
Yeah. This up here for n1. Yeah. Right. And that tells us this last term, right? This last term is less than
Yeah.
epsilon over
Okay.
2.
Yeah, that's true. And
Right.
then for that one, for the other one, let's see. So
So this is all the extra. So this is like if I make it like if I make m capital N, right? Then this is all the stuff after capital N up to that point.
right, right. So
Yeah.
do we know that M, like capital M, is greater? Oh yeah. Oh wait, no.
We know. I think we know.
Oh.
We know this, right?
We know that. Yeah, it's true. Yeah, because if your function f would be the identity up to n.
Right. Exactly. That's what I was thinking as well. Yeah. Exactly.
Then it would be that number, and if it's not the identity, then it would be a number greater than n.
Exactly.
Because you need n, no?
Exactly. That's what I was thinking too. So we do know that, although that's not actually stated, but it is true. Like it's not stated in the book, but it is true. So with that, we know that first of all, we know that this is small enough. So we can right away put that this is epsilon over 2, right? And then this one, this is what's left over extra, right? And so this is certainly going to be, well, how should we say it? It's because it's like this extra, I think this extra is less than or equal to the sum m, k goes from m plus 1, n plus 1 to n, or to m, I guess.
Yes, small m, yeah.
Of a k.
Well, absolute value of a k, right?
Of absolute value of a k. Yes, right. Yeah, that must be true. So, and we know that, so I guess what I can do here is I can just kind of put, so I don't actually know the value of that extra, but I know it's less than this. So it's going to be, Sn plus that, and that is going to be Sn plus epsilon over 2. I guess strictly less than, right? And so then that takes this to be epsilon over 2. And so then we get that this is epsilon.
Right. Yeah.
Yeah. There we go. So I'll add that to my notes too. My notes don't have that, what I was saying here. I just kind of said that this was less than epsilon over 2, but I didn't fully understand that. But hopefully that makes sense now also, to Daniel as well as you're listening. If that makes sense, that this is epsilon over 2. This is definitely epsilon over 2, but this is also epsilon over 2 because it's the extra. It's less than the extra. And we're done. So yeah, I do just a little bit feel like the textbook proof had a few sentences missing, but that's always what it is with.
Yeah, it's up to the author to decide.
Yeah. Right. That's the classic thing. Daniel, okay with this proof? Okay, perfect. That's honestly, that is kind of the goal. I don't just want to sit here and recite to you the book, right? I want to make it more clear, or I want to do it my own way, just like with my slight differences or slight extra explanation, things like that. So I'm glad to hear that it makes more sense than what was in the book. That's great. Okay, so well, let's continue. I was thinking we maybe do. I wanted to try the ratio test. I'm gonna be honest. I haven't even fully read the question. But I know it's prove the ratio test, right? That's what it's gonna be. That's what the question's gonna be. So I think that's kind of fun. Although maybe it would be fun to just try this question first and just see if we can apply whatever we know to this, and then we can, move on. Hopefully nobody has any objections to that. So that's what we'll do. We'll do this, and then we'll do And then we will do the ratio test here. Okay, so decide whether each of the following series converges or diverges. So we have like a whole bunch of things here, right? And then we want to, figure this stuff out. So okay, so we need to apply, we're going to have our tests available to us here, right? So we have our let's just get all the tests, right? So the tests are the Cauchy criterion, which I don't think is going to be directly very helpful. We have this guy, we have this guy, we have this guy, we have this guy, and that's it. Or, well, no, yeah, that's so we have those kind of tests, and I'll just kind of put them all here. So the first one, these are all our tests. Let me just put them all here first. Okay, so clearly the series is not alternating for the first one here, so we don't need the alternating one. For the first two, it's not alternating. These ones are all alternating, right? So maybe the alternating one will be helpful here. I don't know. We'll see. The first one is 1 over 2 to the n plus n is what we're summing, right? So my instinct is to compare this, right? So we can do a comparison test. So I think it does converge. So we have that 1 over 2 to the n plus n is less than or equal to 1, no, is greater than or equal to 1 over 2 to the n. No, it's less than or equal
to. So if you put a smaller denominator,
yes.
then you have a bigger number. So
right. So
it's greater than or equal.
Oh, so it's great. Yeah. Hold on. So it's this number is bigger.
Oh yeah.
Right, like that. This is how I have it. Yeah. This is true for all. Right, because this is going to be like 10 when this is just 8. So this is going to be smaller. Yeah. For all n greater than or equal to I don't know 0 or 1 or something. 1. Right. So that means that the comparison test. Oh, and sorry. And to be clear, the series 1 over 2 to the n converges to 1 over 1 minus a half or something like this, right? So it's going to be
1 here.
Just 1 here. Why 1 here?
Because we have k from 1.
Oh yeah. Sorry. Yeah, you're right. From 1 to infinity. So I'd need to like translate it down, right, or by 1 or something like this. But so okay. So let's just do that, right? So the actual statement of the convergence here, where is it here, is like this. We know this much. If with the condition that r is absolute value less than 1. So this is going to be, we can do a little bit of a, this is going to be the same as the sum k goes from 0 to infinity of 1 over 2 to the n minus 1, right? Because, sorry, I said that kind of loud. We have, we just have to subtract what's going on at 0, and that's going to be the same thing. So this is 1 over 1 minus a half minus 1, which is 1. Okay, so that converges to 1. And so by the comparison test, if the bigger one converges, then the smaller one also converges. So by, 2.7.4, 1, the series 1 over 2 to the n plus n converges. Okay. That's all for that. The next one's very similar. So I'll kind of just squeeze it in here. So I'll do a different color maybe. For B, 1 over, well, I already kind of jumped the gun, but anyways, sine n over n squared is less than or equal to 1 over n squared for all n greater than or equal to 1. because sine n is less than equal to 1. 1 over n squared
By
converges.
the way, here you can apply the comparison test.
Here you can what, sorry?
You can't apply the comparison test because you need the smaller sequence to be non-negative, and the sign kind of like oscillates between Instead, what you can is take absolute value of the sign, right, and then it's definitely
And
it
then
definitely works, and then you use that test, the absolute one.
yeah. Okay, let's actually write that. Yeah, that's true. That's true. I don't know. I didn't see that detail yet. So okay, so if the series absolute value sine n over n squared converges, then the series sine n over n squared converges. Okay, so that's for B, right? So that's this guy. So now we show that this converges, and so the series sine n over n squared, in absolute values, is equal to this. And so this this is less than this, right? And this converges, and so this converges, but I guess that's what I really should be saying, right? Well, not really, but okay, then, let's just say, let's say this, right? So for all n greater than or equal to 1, this converges, and it converges by the p-value test here, right? So we have this converges if and only if p is strictly greater than 1, which is true.
Also, by the way, they have to elaborate the derivation for the convergence of this one specifically in the book, like before even this test.
Sorry, say it one more time. What'd you say?
Like one of the first few things that they show when they start with series is proving the convergence of the reciprocals of the squares.
Right. Yes, that was earlier, right? That was earlier in the 2.4, I think, or something like that, right? Yeah, exactly. And then do we need to show that this converges as well? No, we don't need to show that that converges as well.
You mean the summation for the?
Well, yeah, that's what we're showing. Like that summation converges, right? Yeah. But we don't need the. Yeah, we don't need to show that. Never mind. Yeah, I was just for a second I was thinking we need to show that this converges, like the sequence converges to 0, and this sequence also converges to 0. But that doesn't matter. It's just the. I mean, they do, right? They do, but that's that it's only relevant here. So, anyways, good. We're good. That's all. So now we can just conclude that the sum sine n over n squared converges. And then we get that this converges. Okay, and then we still have these alternating ones. So these are all, no, they're not all alternating. That one has a plus there. Wait, hold on. Am I looking at something wrong? No, that's fine. Yeah, so positive.
So you add two times and then subtract the.
Oh yeah, add 2 times, subtract once, and then add 2 times, subtract once. Yes, okay. Anyways, let's look at C first. So what's going on? Well, the denominator keeps going up by 2, and starting at, well, I guess it depends on 2 over 2, and then this one keeps going up by 1, right? So this is the sum. It's going to be what? It's going to be 2 plus, assuming n starts at 1. So it's going to be, 1 plus n over 2n.
None, right? Because 1 plus 1 is. Oh yeah, it's true.
Right.
Yeah,
n plus 1, and then we got a negative 1 to the n plus 1. n plus 1.
The
Yeah.
n. Well, yeah,
N plus 1, right? Because then 1 and it's 2 and it's, yeah, right?
Yeah.
Right. Okay. And so we need to decide if this converges. So, okay.
So I did it a long time ago, so I don't remember now.
Yeah.
But basically, I think what I did was taking the partial sums. Like I did it just the raw way. I think I took the partial sums and then n plus 1 over 2n, I kind of distribute that division over there. And I
Mm-hmm.
get some kind of like a bunch of 1 over 2s added up or something like that. Oh, well, with some negative signs alternating.
Yeah, right?
Um,
But then you're going to have a bunch of 1 over n's also alternating.
yeah, and then what did I do?
Okay, well, let me just bring this down a little bit, right? So this is for C. So, yeah, so this is the series, and whatever, 1 to infinity, let's just say. And then we can say like this is like a half plus 1 over 2n negative 1 to the n plus 1. All right. And then well, we can just take the half out, can't we? We can just take the half. Oh no, but that's if it converges, we can take it out. Sorry. Right, that's if it converges.
I think that's why I used the partial sums so that I could take the half out.
Okay. Right. So this is let's just say this is the limit as the 1 to n, no, m, limit over m of you take the half out, so we have 1 plus 1 over n and then negative 1 to the n plus 1, right? And then this is lim, I mean, you can take the half out as well. Can I take the half out? Do we know? No, I can't take the half out, right? So I have lim m half. What do I need to do now? I need to
I mean, I think definitely you can take the half out because it's a constant, so it will not affect any convergence.
even if we don't know the limit exists yet. Yeah, we can.
Well, okay, assuming that it exists, right? Okay, sure. But well, I mean, like, sure. Okay. Let's keep it there.
Yeah, right. Because we can't assume the limit exists yet, right?
Well, but then you are also manipulating the limits as if it exists.
Well, have I yet? I don't think I have done that yet. Have I?
Okay, sure.
Right? Yeah, that's the only thing. So, okay. So then, now I need to figure out what this is. So, okay, but I mean, I can break this into now. This is like the sum 1 to m of negative 1 to the n plus 1 plus the sum 1 to m 1 over negative 1 to the n plus 1 over n, like this. Yeah, but now I want to distribute the limit, right? But that doesn't exist, does it? No, it doesn't exist, does it? I don't think so. Yeah, that doesn't exist.
Yeah.
So since I want to say since that doesn't exist, then diverges.
Wait, is that true? Yeah. So if you take, okay, let's see. If you are arbitrarily close to 0 on the right side, on the right term, like negative 1 to the end, right? If you are arbitrarily close to it, you can always get outside it, right? And you can, and like frequently, so that means all the time, you always get either, so you're close to 0, right? And you can be close to 0 either on the left or in the right. But anyways, when you add 1 over 2, what happens? Actually, when you add 1, oh well, when you add 1 over 2, you basically get arbitrarily close to 1 over 2 and also arbitrarily close to negative 1 over 2.
Mm-hmm.
So basically, you have two subsequences whose series converge to different values.
So it diverges.
Yes.
Okay.
Like I'm not sure if they put it as a theorem in at that point in the book, but definitely it's true, right? If you have two subsequences that when you take the series, they converge to different things, then
Yeah, it's here. Like this theorem is here, right?
right. And well, you can do it over the partial sums, I guess.
Yeah.
Oh wait, no, because the thing is like I'm not doing it over the partial sums, right? I'm doing it over. Oh no, yeah, sure.
You are
I'm
doing a
doing it
push,
over the partial.
right?
Yes,
Yeah.
yes.
Okay. So I'll call it there. Yeah, that makes sense. That's good. Okay, so I think maybe now let's move on to, well, I don't know. Well, we've been doing this for an hour now, so we can either do the ratio test or we can move on to 2.8. Why don't you guys take a vote? There's only 3 people here, so it's not the most exciting vote, but like I'm good with either. Maybe we take a 5-minute break no matter what, but not even 5 minutes. Take it. Well, we can, whatever, 5-minute break, sure. I don't know. What do you guys think? What do you want to do next? Do you want to move on to the ratio test? We give it a shot. It might take us a little bit of time, and then do a little bit of 2.8, or we just try to now start tackling 2.8.
I'm okay with the ratio test first.
Okay, I'm also good with ratio test. Daniel, are you okay with let's start the ratio test? Okay, so we're all good doing the ratio test. That's good. Okay, so let's start it. I don't know. We can take a break in just a few minutes. Maybe let's just start. Let's just talk about it a little bit, and then we'll see how it goes. Or we can do it. I don't know. We'll see how long it takes. I don't know. So, given a series with that it's not identically 0, right? Like that like not every sequence is 0, or I guess not any sequence, not any value is 0. I don't know if this means an is not equal to 0 for all.
I think they mean they're like all elements, but technically it's enough if only a finite amount of an are equal to 0, right?
Yes, right. That's what my thoughts as well, right? So, but yeah, I think they mean here that, for all n greater
Sure,
than equal to
because
1.
if there are a finite amount, you can just remove them and it doesn't change the convergence.
Right, exactly. The ratio test states that if an satisfies this, so the limit of ratio of successive terms, absolute values, is a number strictly less than 1, then the series converges absolutely. Okay. Now we need to show this fact, and we will show this fact by this. Okay, so let R, I guess it gives you a little basic rundown here. Let R prime satisfy R is between R prime is between R and 1, so this ratio converges to R. R prime is between it. Explain why there exists an n such that for all n greater than or equal to n, this is true. Okay, I don't know, and we'll see. Why does the absolute value of an times this converge? Well, that's pretty clear because that's just a geometric series with R prime less than 1, and then that's just a constant in the front, right? So we can do that. And I guess show that this converges. Well, if this converges, so show that the absolute value converges, and that the original series converges. Okay.
So that last step is just trivial from the absolute convergence test, right?
Oh, right. The very last step, because if this converges, yes, then this converges. Right? That was the absolute convergence test. Let me just remember what the absolute convergence test is. I did not write it in my notes for some reason. I think it's here, though, right? Absolute convergence test. If the series that converges, then the other one converges as well. Okay, so that very last step is completely trivial, but we have to show that this converges, and then well, assuming we'll use these other parts here. Okay, so let's just give it a shot. Let's see what happens. So we have that, okay, so we have that the series an, n goes from 1 to infinity. We don't know anything about it, but we have a series. We know that for all n greater than or equal to 1, an is not equal to 0. Okay, and we know that the limit of over n of the absolute value of an plus 1 over an converges to a value r less than 1. Like strictly less than 1. Okay, so they're not equal. The ones, and so we know, of course, that there is a r prime, a real number r prime, that satisfies that it can be between these two numbers. So let r prime be a real number such that it is in between, so that exists. Okay, so show why we can have this, right? So well, we know that the limit over n of the absolute value of an plus 1 over an converges. So that means that for all epsilon greater than 0, there exists an n in n such that the absolute value of an plus 1 over an, well, the absolute value of that minus r is less than epsilon. So we can pick epsilon to be r prime, I'm pretty sure we need to do here. Maybe we actually, yeah.
Quick question. Is that correct from the language perspective that the limit, saying that the limit converges? Like, I mean, you either say that the limit is, you either say that the sequence converges, or that the limit is, or that the limit exists.
Yeah, I guess I would just say like the sequence you could say the sequence converges, right? Which means the limit exists. I guess. Yeah. Okay. Yeah. Exists. We can just say exists. Yeah, true. Well, okay. I mean, I could just even is r, right? It's equal to r. And so then let epsilon be r prime. So then we know that for all n greater than or equal to n, right? So then I think this is probably enough. We can kind of break this into an plus 1 over an minus r less than r prime. And then, like, can we do something here? What are we trying to show? We're trying to show this. So, so I probably have to pick this to be 1 minus r, I think. 1 minus r prime. I think I should pick that to be 1 minus r prime.
I guess perhaps, like this choice is too arbitrary. So in my opinion, I would just first apply the triangle inequality on that absolute difference there.
And what would that, and so that what would that do? Sorry, it would say that.
Oh no. So no, that doesn't help honestly, because then you don't have any bounds on that summation. So instead, I guess that you can just expand the division over an on both terms, and then take an out, like the 1 over an.
Okay. So this is going to be the absolute value of of 1 over the absolute value of an, right? Times an plus 1 minus r an.
Yeah. And then that's less than epsilon.
But I chose that to be. Well, okay, so then never mind. I don't have to pick that. I can just pick that to be. I can just pick that to be 1 over a n or something like that, right?
So well, can you so what is no, because I think they ask you to show that is for every an, and you don't have any monotonicity. So I guess that you actually have to choose something like 1 minus r, or as you said,
Yeah. Okay.
but but you can come up with that later, right? Like just manipulate it with epsilon, and then we can figure out exactly what epsilon is it.
Yeah.
So
Right. So this is r
so
plus.
so so the 1 over n that is being divided. Okay, yeah. So that 1 over n can go multiply to the other side, and then that absolute difference is not great. Okay, yeah. So,
Uh.
so like now what I'm saying is you're subtracting r times a n from a n plus 1, and is that always less than the absolute value of a n plus 1? No. Oh, no, no, sorry. Is that always?
No. Right.
Uh,
I
maybe.
don't know exactly. So this is, so we can do like, this is an plus 1 minus r, an less than, yeah, whatever. This is what you said, right? So like this. But this is okay, this is fine. So then um, and there is an, and yeah.
But I actually don't know. I think I'm a bit lost.
But we almost have it, right? Because this is what we need to show, and that's like almost what we have. We just need this to be 0, don't we? If that was 0, no, but how would the absolute value be less than 0?
Yeah, indeed.
Yeah, hold on, that wouldn't make sense. Okay, so this is what we're trying to show, which is the same thing as this, which is the same thing as, this, but I don't know if that makes any difference. Whatever, an less than equal to r prime, which is, less than 1. So we need to show that this is less than or equal to. Okay, but r prime is really the important thing, right? Yeah. So then we can choose, like, can't we choose r minus r, or r prime minus r?
Yeah. Okay. So I just proved it by contraposition. Um, so I can show you that if you want. Like I was following on my own.
Yeah. So how contraposition? Like,
So yeah, I assume that for every n, for every big n, there is always some small n after it, for which that inequality over there is not true.
uh-huh.
And I think if you show it graphically, so you can draw the number line, you can draw r prime, and 1,
Mm-hmm.
and then that it would be, yeah. So the epsilon that you have to choose is, I guess that is r prime minus r. But yeah, like here, what happens is
Yeah,
the following, right?
that's what I said
For
here. Right?
every
Yeah.
n,
Yeah.
okay,
Right.
okay.
Right. Yeah. But go ahead. Yeah.
So yeah, so for every n, assume that there is always some small n after it, for which an plus 1 taken absolute value is greater than absolute value of a n times r
Mm-hmm.
prime.
Mm-hmm. Mm-hmm.
That means that a of n plus 1 divided by a of n absolute value is greater than r plus 1 than r prime,
Yeah.
right? So it will be in that second interval,
Yeah.
and it cannot get arbitrarily close to r.
Right. Yeah.
So
Yeah.
that
Yeah.
would be,
I'm following. Yeah. And I think this is the same. I think just if I pick this value, I think we can work it out here as well.
probably.
Just instead of doing it the other way, instead of
Yeah,
contradicting.
yeah, sure.
Yeah.
Okay,
But
yeah.
like, I think we are honing in. We are converging onto the same thing, but just from different directions here. Because I also right at that moment was like, oh, you just pick r prime minus r, right? Because then we want, okay, so for all epsilon greater than 0, there exists an n and n such that this holds. So if we pick that, right, r prime minus r, so then this is the distance from this to this. Yeah. So right. So if I pick here now, this is r prime minus r. So this still holds, right? Everything still holds. This is all for n greater than or equals
Yeah,
capital N.
but how does that help you to show that that it's true for every epsilon. You are picking a specific epsilon.
But I don't need to show it's
Mm.
true for every epsilon. I just need to show that it's true that there exists an n,
Okay, that's true. Yeah, sorry,
right?
I kind of forgot about the statement. Yeah.
Right, right, right. That there is some n such that as long as we're past that point in the series, this holds in the sequence.
Yeah.
This holds, right? So I think now it kind of just works out. I think if I do, yeah, it does, right? So I can do. This is what am I doing? Absolute value a n plus 1 minus r a n less than a n r prime minus a n r. Oh, what happened? Oh, no, nothing happened. Yeah. So, and now, I mean, I really just want to, but does the absolute value do anything here? What's happening?
Well,
So,
we know that r prime minus r is positive, so definitely, I guess you could just put absolute value on the right hand side if you want to.
like, I can just put that there.
Yeah.
Yes, right, because this is positive, right? And so, well, yeah, well, it is strictly positive. So then I have this, but what does that mean now in terms of like I can't just get rid of the absolute values now, can I? Or maybe I can. If
Well, okay, sure. I mean, you can get rid of the left hand side absolute value because because it's either true that way or it's true when it's negative. So it will always be true without the absolute value.
so I
Because the
can
right
get
hand side is always correct.
get rid of a and like I can just write it like minus r like this, but I need to keep this one.
I mean, you don't have to because you know that r prime minus r is positive.
Right, it is positive. Right. Okay, and then we got it, and then that's it.
Yeah. Cool.
Okay, so that's it. So that's the kind of a direct way. You just choose this epsilon, and then you have that there. So that's good. So we have this. We have that there is an n such that this is always satisfied. Okay, why does this converge? Again, I think I mean unless I'm underthinking it, I think it's very clear why that converges because that's a number strictly less than 1. It's a geometric series. It will converge, and then that's a constant. So yeah, why would it?
Yeah, like in a way, it doesn't relate at all with the first statement, with the first with the item A, right?
Right.
As in, like, it doesn't use at all that fact.
Okay, so I'll just say clearly. Hopefully that's okay, because that's kind of that constant that converges. So it converges. Okay, so then for C we need to show that this converges. So show that the sum n goes from 1 to infinity of the absolute value of a n converges. Okay, so I think, well, okay, so I mean, this is definitely relevant because why is that relevant?
Yeah, because you can replace every every absolute value of a n, like after the capital N, right? You could replace everything with absolute value of a n times r prime, and then you could also actually you could replace it with with what? You could replace it with absolute value of a n capital, right, like the n capital.
Yes.
Times r prime to the power of the difference between
Uh-huh.
n and capital N, right?
Right. And then we do like a comparison test, and we have that the bigger one converge.
And then and then you just have exactly the convergence series. So
Okay, so
I mean, yeah, definitely the comparison test as well.
yeah. So let's do this then, right? So show this converges. So we'll consider we know that for all n greater than or equal to n, okay, what do we know? We know a couple things. So we know that the limit over m or over n, whatever, of a n plus 1 over a n equals r. We also know that r prime is here. Maybe I'll just put a semicolon or something. Is here. And we also know that that for all n greater than or equal to n, a n plus 1 is less than or equal to is what it was, right? We just have less than here, but I don't know if that matters. We just have less than, I don't know. But less than,
we have less than or equal to, right?
do we?
Yeah, I think I just read it.
I didn't.
You mean, sorry, you mean here.
Here. Should it just be equal? You know, should it just?
So
A little strange. I don't know. Yeah, I don't have.
yeah, it seems it's less, it's strictly less. So I'm not sure.
Why don't I take just a peek at the solutions and see if they have less than or less than equal to. Where are we? Where are we? Here we are. Yeah, the solutions just have less than. They don't have less than equal.
Yeah, I guess the book was just
maybe. Yeah, the
like it's definitely is it true if it's equal? So like so if every so like suppose that r prime is 1/2. No, yeah, I think it has to be strictly greater because we have r prime strictly greater than r. So like if it were equal, it would mean what would it mean? It would mean that
r prime is equal to r.
Yeah, exactly.
Right.
Like beyond, like after the capital N.
Yeah. Okay. Okay, so we know that for all n greater than or equal to capital N, a n plus 1 is strictly less than a n r prime. So specifically, that means like a n plus 1 is less than a n r prime, but then I can multiply everything here by r prime, and so then this is less than a n plus 2, and then I can multiply everything by r prime again, and this is less than a n plus 3, and so on.
Yeah, you missed the prime on the n plus 2?
Yeah, right, that's supposed to be a prime. Yeah.
Yep.
And so on, right? Whatever. So that means as we keep going, it's less than so in general, a n plus m is less than a n r prime to the m.
Right. Yeah.
For all m greater than or equal to 1, I guess.
1, I guess, yeah.
1. Right. Yeah. Okay, so then what can we do? We can say that the sum, right, n goes from 1 to infinity of the absolute value of a n, okay, is equal to, okay, so we can say this is
I guess take it up to big N and then take the other part separately, right?
Like you're saying just split this into the sum n goes from 1 to n of a n plus the sum n goes from n plus 1 to infinity
Yep.
of the absolute value of an. Okay, so this clearly finite, right? Oh, I have a cat meowing. So that's clearly finite. And then this, we argue, is... okay, so we say that this is... Can I just say that? And then this is like, some finite, let's just say equals capital K or something, right? K plus the sum n goes from n plus 1 to infinity of, or I guess I could just say n goes from 1 to infinity of a n plus n. Well, this is just equal. Like I haven't done it. I haven't done anything there, right? And then this is k plus, this is now less than k plus the sum n goes from 1 to infinity of absolute value of a n r prime to the n.
Yeah.
N, right? Yeah. And I get that that is the same as this, but why can't I just pull that out? I guess I don't need to pull it out. I guess I don't need to, like this, I'm saying. This capital A.
Yeah, you don't have to.
I don't have to.
Actually, even the one like the geometric series that appears on
Right.
the book is the general form where you have some coefficient.
Right. And so that would look like that.
Almost, because you are starting from 1, right? So you have to.
Oh, did I do that again? Oh yeah. Okay, well, it'll be approximately this. Whatever. Some plus or minus 1 or something, or plus or minus an or something like this. But anyways, it definitely converges. That's all that really matters, right? Definitely converges. And so by the comparison test, tells us that the sum n goes from 1 to infinity of a n converges. And there we go. And then, as we discussed, this is basically a theorem already stated. And there we go. That's fun. I like that. I liked
So basically the remark is that if the ratio converges, if the ratio of adjacent elements converges to a number less than 1, then I mean the ratio, the absolute value.
Yeah.
Less than 1, then the series converge.
Exactly.
Converges absolutely. Right.
Converges absolutely. Yeah, exactly. Okay, that was fun. I like that. I'm glad we proved that together. Again, that was like, I remember this so distinctly years ago in Calc 1, having to prove that certain series converge using the ratio test, and wondering about the proof of it. So there's my many-year goal achieved of proving this. Okay, guys, so let's take a few-minute break. Sorry, you gonna comment? No? Okay. So let's take a few-minute break, and then we can start 2.8. Does that sound good to everybody? So 5 minutes maybe? I still have some energy, if everybody still has some energy to go. So let's break until, for me, it's 6:42. So that's 5 minutes. Okay, guys. If everybody's back, I am ready to go. So, okay, awesome. Daniel, hopefully ready to go as well. I'll trust. Okay, so let's do it. So I'm recording again, and you see my screen, and we're good. Okay, so so far, enjoying what we've been working on. Let's take a look at 2.8 now. And so again, 2.8 is talking about these double summations and products of infinite series. And really, it's a bunch of kind of guided exercises or guided theorems through a bunch of exercises. So what I'll probably first do is I'll just show the theorems, and there's not that many, and then we can kind of try to do some of the exercises. I think there's basically 2 theorems here, so let's maybe just like take a look quickly at it. There's nothing else to really do. Okay, so first of all, you know, if we have a doubly indexed array, that's the first thing we're going to talk about. Doubly indexed arrays, it doesn't make sense to the iterated summation. Don't in general match up when you add it, you know, along the columns first or along the rows first. Or I guess the other way around. But anyway, so it's they don't in general add up. They're not in general equal. I mean, so we need you know, to figure out some way to define this summation, this infinite summation of this doubly indexed array. And so one way to do it is to kind of imagine these rectangles, right? So when we talk about a doubly indexed array, you can kind of, like, in my head, I kind of have like an infinite matrix that I'm kind of imagining, right? So I have, it's from 2.1, so we can kind of look here, right? So a doubly indexed array is kind of like this. It's like it's like an infinite matrix where this is like A11, this is A22, A33, this would be A12, A13, and so on. And so with that in mind, right, we can imagine kind of like the first rectangles. Why don't I use the picture actually, right? We can imagine defining summation of this by taking, you know, let's say SNN to mean, you know, the summation of everything up to ANN, right? So this is ANN, let's say, right? And so it's like kind of the summation. And that's a finite sum, so the order doesn't matter there, right? The order makes no difference. You can add along the rows or add along the columns first, and it doesn't really matter. So this is the sum ij go from 1 to n. Yeah, of a I j, like that, right? Essentially. And this is a finite sum, so the order doesn't matter here. And so we can just say that the limit of this is our definition for the infinite sum, the limit of this. Okay. And again, we'll maybe, yeah, we could do this now, I guess. Using the particular array from section 2.1, compute this limit. How does the value compare? So why don't we actually do it? And then we'll get into the actual theorem here. So just as an interesting example, using the particular array, so that's this guy. This is the particular array from 2.1. Compute this limit, right? So SNN is the sum. Let's just use the actual very precise way that they describe it here, right? SMN looks like this, right? Okay. So this is the sum. I goes from 1 to n. The sum j goes from 1 to n of a I j. And so, you know, again, we can kind of like imagine it like this, right? So what's going to happen here? Well, maybe we can do one more just for the sake of clarity, like this, right? We can go like that. So the summation of this is going to be, well, we're definitely going to have at least -4, right? We're going to have -4. And then these additions like this. But I guess we can go just as it says. Let's just go as it says. So is there a direct formula for Aij that they give there? Do they give a... Yeah, they do, right? Okay, but it's a little bit like, you know, it's a little bit complicated.
So basically, the generating rule is to go with -1s in the main diagonal and then fill into the right of each of those with the descending powers of 1/2 or ascending powers of 1/2, I guess.
So this is going to be, so you're saying this is going to be like, so like do the diagonals.
I think I first, the way I did it was fixing I, right? Or the way I think about it is that you can fix I and then it's kind of simple because then you would have like if you ignore the negative ones, then you would have a bunch of powers of 1/2,
Yeah.
like from the first power of 1/2 up to the power j minus um, minus I. So 4 minus 1, yeah.
Right. So the sum I goes from 1 to n, and then here we need to sum across all these things, right? So ignoring the -1 for a second, we just have 1/2 to the
J minus I for every j from 2, from I plus 1 to n. Right?
yeah.
I mean, you need another summation.
Yeah, I need a summation, right? That's what I'm kind of, yeah, okay. So j goes from I
Plus 1.
plus 1. Why I plus 1? It goes I plus 1.
When I is 1, you start from 2. When I is 2, you start from 3. And when I is 3, you start from 4. So I'm basically fixing the row first.
Yeah, and this is going to go from I plus 1 to what? Sorry?
To n.
To n.
Yes.
Okay, because this is going to be, so like for...
Because when I is j, then you have -1. And when j is less than I, you have 0. Actually, it follows, like, even if you write the definition, like the algebraic definition, it follows from there as well.
So here I can just put 1/2 to the
J minus I.
j minus I.
Yeah. Or if you want to, 2 to the I minus j. And it would be this.
Yeah, right.
Yeah. And then that's a geometric progression. Like for a fixed I, you basically you're adding from 1/2
Mhm.
to 1/2 to the power of n minus I.
Right. So this is there's some formula for that, right? For the finite sum, right? There's the where is it? Oops. It's in this last bit here, I think. It's the finite sum is that, right?
Yeah.
So if that's our this, then this is our this. So then there's a little bit of rearranging that needs to do, right?
Yeah.
Needs to be done. So this is going to be, this is the sum.
You just set R. I guess you could set R to be 1 over what?
Well, we need this.
Yeah, like here you're basically adding from 1/2 up to 1/2 to the n minus I power, right?
Well, this is gonna from 1/2.
So here n minus I basically, and R is 2. It's 1/2. I mean.
Yeah. Okay. So this is. Oh, I have it here. So. Okay. So it's gonna be 1/2, and then we're gonna have here j.
Well, what I did was just taking what is the first value of this difference, j minus I? Well, that's 1. And what's the last value? Well, that's n minus I. And then I just apply the formula. So I'm adding from 1. So I just have to take. So perhaps I can write it here. Like
yeah, I maybe write it. Yeah.
I'm trying to write LaTeX at the same.
That's okay. That's fine. That's good. You can write LaTeX.
So you're basically adding from 0 up to n minus I minus 1 frac 1/2 to the power of R. Well, not R. Let me call this. How should we call this? We should call it probably K, and this is K. Does this work? Like I'm not sure. Does this render LaTeX?
I don't think so, but it's okay. I'll read it.
Okay.
So yeah, you take the half out, and then the sum K goes from 0 to n minus I minus 1. Oh yeah. Okay. 1/2 to the right. So but I just called it J, but whatever. So it's like J goes from 0 to n minus I minus 1, and then this is going to be 1/2 to the J.
And you need to take 1/2.
Oh yeah.
Right.
Okay.
Now just apply it, and you get what you get.
Yeah, what do you get? So this is going to be the 1/2, and then you have I goes from 1 to n, and then here you're going to have 1 minus R to the n minus I minus 1 over, but r is a half, right? And then this is going to be a half. And so those halves kind of go away, right? So we just have this.
Well, are you sure in the formula it's not up to n plus 1? Like, sorry, up to n minus 1 on the
Maybe.
on the book. What you copied, it should go to n minus 1, I believe. Like,
Yeah, n
yeah,
minus
it
1.
is.
Yeah. Okay,
Yeah.
so
So,
this should be, so this should just go away like that?
yeah, yeah.
Right?
And then you have basically the same thing once again. Like, you can take that one and that. Um,
Yeah, right. So this is going to be n minus the
and now your
sum.
summation, right? So where does it go from? Like when I is 1, it's n minus 1, and when I is n, it's 0. So it's basically going from 0 to n minus 1, 1 over 2.
Yeah.
And I mean, like it's just simpler, and at least for me, to think about it that way rather than just doing the algebra.
Yeah. Right. So then this is n minus
And then it's like 1 minus 1 over 2 to the nth power.
oh yeah. 1 minus 1 over 2 to the n
Yeah.
over
Over 1 over 2.
1 over 2. Yeah. Okay. And then so this is n minus 2 2 1 minus 1 over 2 to the n, let's just say.
You're missing one parenthesis there, I think. Or 2, at least.
Like that.
Parenthesis.
Oh no.
Yeah.
Like that.
Yeah.
Yeah, right? That, yeah. Okay. And then but this doesn't the limit of this of an n, right? So
it's n minus it's n minus 2, right?
why is it n minus 2? Oh, because
Well,
this here, because so it's n, like it should be n minus 2. Or no. This summation,
no.
this is an n here, right? But then just because minus 2
Yeah.
here, like this.
Yeah.
Yeah. So it's n minus 2 plus 1 over 2 to the n. Okay, but that doesn't converge. Does it? No, it doesn't converge. So does that mean that this doesn't converge?
Should, right? I think this example, the 2.1 example, is an example of a non-converging to the
Okay, right. So
okay,
this diverges.
Yeah.
Yeah, okay. Makes sense. Let's see, is that matching what I have the solutions? Let me scroll to it here. Oh no, here it gets, they get -2. But they have
Right.
almost the same thing here. They have this honestly. 1/2 0 to n minus 1.
Oh wait, yeah. Remember that we actually forgot to subtract. Like we didn't include the negative ones, right? That's it.
Which
Like,
ones?
the main diagonal of the grid.
Ah, yeah. Right. So these ends will all go away.
Yeah.
Right. These ends will all go away. And this, yes, right, converges to -2. There you go. Okay. There we go. Yes. Little sloppy, but anyways, that's what's happening. Okay. Great. So, moving on. That was that. So now we see the way it compares is that what did we get here? When you went across the what is it? Columns, sum across the columns first, you get 0, and here you sum across the rows first, you get -2. So this is the same as the result from when you get -2. When you sum across the rows first. So this was JI. Okay, whatever. Interesting. So now let's see what the thing is, so there's an exercise, but the actual theorem, and I'll just kind of isolate the theorem here and read it, and we'll maybe just for a moment go past the proof. But we have a doubly indexed array. If this double summation of absolute values in this order, so columns first and then rows, then both the two iterated series converge to the same value. Moreover, the way we've defined the limit of these partial sums, essentially these squares of partial sums, is all the same thing, right? It all turns into the same. It's these values.
How again do they show? Do they define convergence of a doubly indexed array?
But do we need that here? I don't know if we need, because
I mean, they are literally saying if this double summation converges, and I'm just trying to remember what exactly that double summation means.
yeah, right. The double infinite summation.
Yeah.
I see what you're saying. So do we have that?
Okay. Yeah, they show it. So in the exercise 2.8.2, right before the theorem, they tell you what it means.
Yes. Okay, great. Yeah, right. Okay. So we'll do that. We'll do that exercise. Right. Okay, so then the next bit is just kind of walking you through the proof, and then the proof ends there. So we'll look at that, but we'll just for the moment skip it. I just want to talk about everything first, so we make sure we get through everything, and then we can try some of it. One final common way of computing a double summation is to sum along the diagonals, where I plus j equals a constant. So that would be like the diagonals like this, like that, and so on. So that's not how we did it here, but that would be another way of doing it. And so you can see it's like 1, 1, 1, 2, 2, 1, and so on. In general, you have this expression for the kth anti-diagonal in a way, but whatever. Represents another reasonable way of summing over every ij. Assuming the hypothesis and the conclusion of theorem 2.8.1, so 2.8.1 is this guy, right? So assuming all that works, show that this converges absolutely. And so if that converges absolutely, then it converges to the same limit, I guess, according to this, right? It converges to the same limit. And then imitate the strategy to show, I guess that's what I'm saying here. Show that this converges to the same limit as what the SNNs did. Okay, so we'll look at that, but I just want to kind of say it out loud first before we do it. And then this last part here is the product of a series, right? So if I have a series and I have another series and I want to talk about the product of these two series, then I can do that using the Cauchy product. Okay, so we have the Cauchy product of two series. And the Cauchy product is kind of this natural way we would just kind of distribute everything if it was finite in a way. And we have this infinite summation of these dk terms, which are exactly the same as how pretty much exactly the same as we've defined this double summation, right? But of that kind of combination of the elements of the two sequences.
Yeah, sort of like a convolution, right?
Exactly, right. It is a convolution. I mean, it's exactly a convolution. And then so then we need to show this is the last part, right? Is just to show that if this converges absolutely and this converges absolutely, A and B, the two series converge absolutely, then the summation of this, the iterated summation converges, and then notably that this summation, let SNN be this, SNN goes to that, and then conclude that this summation with these dk's also converges to that, essentially. Okay, so really, like, the key thing is just like, how do we do it? How do we have a product of series? That's how. And what can we actually say when we have a product? Well, that it's equal to this SNN and so on. Okay, So with our time remaining here, we can, it'd be nice to go through everything, but I mean, we could do whichever. I guess it would be good to do this exercise here, to maybe start with 2.8.2, and then we maybe better understand this theorem, and then we can maybe take a look at the proof. We'll see how much time. I don't know. We'll see how it's going. I am recording, right? That's a good thing to check. Yes, I am. So 2.8.2 is this exercise, and so let's try to work on this together. So show that if this iterated series converges, which means that for each fixed I, the series that, fixed I, this series converges to some real number bi, and that the series of all the bi's converge as well, summing over the rest of the i's, then the iterated series converges by the same meaning, right? So this converging means that this converges. So it's equivalent to our theorem we had before, which was which was this guy. If the absolute value converges, then the original converges. So we have the same thing here. If the absolute value converges, then the original converges as well. Okay, well, that's good, but let's do it. So, okay, so we want to, so we know that this converges. The sum I goes from 1 to infinity. The sum j goes from 1 to infinity of a, I, j, converges, which is if and only if, for all I greater than equal to 1, the sum j goes from 1 to infinity of the absolute value of a, well, let's just say like I, or something like that, right? I, j, converges. Well, that also means...
Well, you actually need to say to what it converges, because you need also the sequence
okay,
of converged values to also converge.
The I, let's say, right? I'll just use the same notation that's there. Let's just use the same notation, right? So the I here, right?
And now you need the summation of the b's to also converge, right?
And yeah, exactly. The summation I goes from 1 to infinity, bi, converges. Okay, so now we need to show that this converges, right? Well, if this converges, then we know that the sum j goes from 1 to infinity of a, I, j converges by the theorem, right? This up here, right? We know that by which one? This guy.
The absolute test.
Absolute convergence test, right? So we know that this converges. Do we know what it converges to? Can we also say it no? This was a discussion before, right?
Yeah.
So, yeah, let's just say it converges to some. Yeah, it doesn't have to converge to the actual bi here. It can converge to something else, but it does converge. So let's just, because I'm running out of letters, so let's just say, equals ci. And so all we really need to show is that the sum I goes from 1 to infinity of ci converges. Okay. So now okay, well, what do we know?
I'm thinking that perhaps you need to use the partial sums, just at least on that last step. I'm not sure. because like the idea that I have, and in a way, it's also some kind of reminiscent, memory of what I did for this problem some time ago,
Hmm.
was that I was using the Cauchy test. And for the Cauchy test, I needed some finite amount of elements or something, right?
Hmm. Okay.
Because yeah, like I'm not sure now. Like
Yeah. Yeah.
I'll think about it.
Okay. So, well, do we know what this is in relation to BI? Like, do we know that, for example, like the sum j goes from 1 a to infinity aij is less than or equal to bi? So I guess what I'm saying is, do I know that ci is less than or equal to bi?
Well, so like the point, I think it's again using the Cauchy criterion. What happens is that in the Cauchy criterion, you will take an interval from m to n, and you will take the absolute value of that,
Uh-huh.
and that will be less than the summation of the absolute values of each of the terms,
Mm-hmm. Which is the bi's?
And then that would be it, right? Because that would be the bi.
So
So like
okay,
yeah, so
so
it's sort of true.
fix
Uh,
fix epsilon greater than 0, right?
yeah,
And then so we consider uh c cm plus 1 plus dot 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 plus cn, right?
right.
um
That's less than or equal to
but I have to say, like, and what is it? Fix epsilon greater than 0. Yeah, okay, whatever. Yeah, okay. All we know is that m is strictly greater than n here, right? That's all. Or other way around. N is strictly greater than
yeah,
n, right?
yeah.
So this is less than the c,
Then individually.
like the
Yeah,
individual like this, right?
yeah.
Plus
And then you
c.
apply the same rule for each of the CM, for each of the C.
So we do know this fact. This is true for all I greater than or equal to 1.
Uh,
Or maybe just the absolute values, at least, whatever.
yeah. My problem is with taking an absolute value of an infinite sum. I mean, it converges,
But it
but we know
converges,
that for
right?
C.
Yeah.
Ah, okay. Like, oh yeah, sure. Okay, yeah, sure. These are real numbers. Okay, sure.
Right?
Yeah, yeah,
So then this I can immediately say is less than bm plus 1 plus dot 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 plus cn,
bn.
bn.
Yeah. And now the fact is that since B is a summation of absolute values, you can take a kind of like a big absolute value and get rid of the individual absolute values, and then that gives you the bound on epsilon.
So what's my next line here? What's the next
So
line of
like
it?
basically B is computed as a summation of absolute values, right? So it's always positive. Each of the B's are positive, so you can just get rid of the
Like these absolute values don't actually, they're nothing.
Yep.
Like, so this didn't even
So
I didn't even need that. Like
and
that.
since yeah, and since you know that the B's converge, you know that that summation is less than epsilon.
Right, which is equal. So which is equal to the bm, like, absolute value plus dot 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 plus bn,
Yeah.
which is less than epsilon, right? Like, or at least, there exists an n in n such that for all m greater than, no, other way around, n greater than m greater than or equal to n, that is satisfied.
Yeah.
Um, and so this implies that this converges.
Yeah.
We're done.
Yeah. That was cool.
Okay, makes sense. So a little bit of Cauchy stuff, but yeah, good. Makes sense there. Okay, good. Daniel, you're doing okay too. Following along, all right. If you have any questions, feel free to use the chat if you have any questions. But Okay, perfect. Okay, let's keep moving. So the next thing is the theorem itself here. So we can do it. I think. And what else is there? That's all, right? Because then it's just the theorem itself, and then another little a thing like this where it's like the product uh, of this, and imitate the strategy to prove that this converges, and then product of series. Okay. Anyways, so let's. Mm, let's see. What should we do next? Well, we can attempt to prove it. I just don't want it to go too long, and then we kind of like don't get to the end of it, you know. But
Yeah, actually, to be fair, I remember when I was doing the problem, the proof for 2.8.1. I think I had to like I don't remember if I tried to find answers somewhere
yeah,
or just a bit of help of Gemini. Like yeah, it wasn't that
yeah,
trivial.
yeah. So and we're approaching the end of the session here. So I'm a little bit thinking, why don't we talk a little bit about the product of series now, because I find that
Yeah.
also interesting, and I do kind of want to get to that. So does that sound good? We maybe talk about this now, product of series, like do some exercises from here. Yeah.
Yep.
Sounds good. So just like the statement of this theorem up here is important, right? So I'll just repeat the statement, right? So we have a doubly indexed array, and then that this doubly indexed array, doubly indexed sum converges, which means this converges for all fixed i's, and then the sum of those i's converge. Those sum of those, the convergent values. Oh yeah, sounds good. Good that it sounds good to you, Daniel. Then both this converges, right, to the same value, and this definition, so these are the iterated summations, right? Then, these are also the iterated summations. This value also converges to the same value, which is this is like the limit of the finite sums. So it all kind of works as long as it is, absolutely convergent in a sense. Okay. So then that's this. Now, product of series. We have this definition, Cauchy product. Let's take a look at these last couple exercises here, right? And see how this goes. So the exercise is, assume we have these. Let me just copy it nicely into a picture. So assume that each of these series converge absolutely to A and B respectively. Okay, show a couple things. Show that the iterated sum converges so that we may apply theorem 2.8.1. And again, we have this definition where it's like this converges for all fixed I, and then what it converges to converges. So it's like the iterated sum. Then let SNN be this kind of progressive partial sum. Prove that the limit of that is AB, and conclude that all this, right, is all true. Now it does say apply theorem 2.8.1, so I'm gonna have theorem 2.8.1 readily available. So maybe I'll just kind of make these a little smaller, just so we can kind of fit everything here. And then I'll put this kind of a little small, but I'll put it there. And then maybe I'll just, for clarity, put a little box around it. That's a theorem. Okay. So so that we may apply. So that this theorem will be for the second part, but just for the first part, we have to have the hypothesis of the theorem working, which is that this converges. So let's do it. So show. So for A, show that the sum I goes from 1 to infinity, the sum J goes from 1 to infinity, the absolute value of A, I, B, nope, I always draw it wrong, J, there you go, converges. Okay, so let's just first of all focus, fix I greater than or equal to 1, I greater than or equal to 1. Then we think about the summation j goes from 1 to infinity of a I b j, and so we can we can
Yeah, we can take AI separately, well, absolute value of AI separately, and keep also summation over the absolute value of BJ, just because we know that the summation of BJ, the series of BJ converges absolutely.
So you're saying I can take this, I can take AI out here?
Yes, because of the constraint that the BJ series converges absolutely.
Mm-hmm. Right.
Like we don't know that it converges to B, like this summation that we have absolute value of BJ, but it converges. Like according to the definition of converging absolutely to something that we already know.
Right, right. So this converges,
Yeah.
and that's all we can say, because that
Mhm.
converges, right? And so
Yeah.
AI times it converges, but I can't
Yeah.
really say what it converges to. But it converges to something.
Mhm.
Let's just say converges to CI.
Yeah.
But actually,
Well,
it's
not CI. It's independent of I, right?
yeah. Well, it's like if I just have AI here, right? Then I can just have like beta, or something, right? Like I can just have like
Yeah.
I just say, well, it's not capital B. It's uh, you know a beta, I guess, right? Beta. So AI times beta. Okay. Then we want to show that the sum I goes from 1 to infinity of the absolute value of AI times beta. Well, this is, beta times the sum for the same reason as up there, AI, which, converges. Okay. So we did that. That's not too bad. Now, well, great, we did that. So we show that this converges. So now we can apply this theorem. We need to show this is SNN. Prove that the limit SNN is AB. Then conclude limit SNN. Yeah. Well, and that's not too hard, right? Because this is the limit SNN. If that's AB, then great. Then each of these. Okay, I don't know. Let's just start with this first bit. So we just have to show that SNN converges to AB. So let's just start with that, right? So SNN, which is the sum, I goes from 1 to n, the sum j, nope, backwards again. J goes from 1 to n of A, I, B, J, okay?
Yeah, the whole point is that this can be kind of like decoupled, and you have a product that goes from one over I from 1 to n over AI, and sorry, like that summation multiplied with the other summation over the
Right, so this is going to be like from 1 to n of AI, right? Like just I, sorry. So just like to really overemphasize here, like that. And then we can rewrite this as this, this. No, sorry. I guess that should be like that, right? And then these are not a function of I, so it can just be taken out.
Yeah.
So then we have j from 1 to n, b j times the sum I goes from 1 to n a I, like that, right? And so we have these
Yeah,
two.
I guess that it's more useful to put the parentheses around the summation sign.
Yeah, like you're saying like all this, so like that and then like that.
No, well, yeah, sort of, but I meant in the last expression.
Sure. Yeah. Yeah. Right. Right. So it's like that, and then
Yeah.
that, like this, right? So just to stay consistent, I'll put that like that. There we go. And so okay, good. So there we go. So that's that. And so this, what do we know now? This, SNN. Okay, yeah. This converges to B, and this converges to A. And so because this is just a like just taking the limit, right? The limit here. We have that as a theorem. If we look at
Yeah,
algebra,
the break limit, right? Or the
right,
break property or something.
we have that right there, right? So each of those converge, the product will converge to the product, and so we have that there. Okay, so then now we know a whole bunch of things, right? So SNN, the limit of SNN, which is AB, is equal to all that. So that's equal to all that, right? And then the only thing left is to show that DK is also that limit. Is that left to show? Yeah, we still have to show that, right? That DK. Do we have to show that?
Yeah, I mean, sorry. I think you have to basically replicate the proof from 2.8.1 to show that.
To show
Because
that.
the proof, to prove that the summation of the decays converges to the same limit, to A times B.
Was that part of
They even tell you that. They even tell you imitate the strategy of the proof.
here, right?
Yeah.
Imitate the strategy in the proof to show that DK converges to the same limit. Yeah. Right. Well, I mean, we like if we just have that, right? Then that will follow suit here. The only thing DK is defined slightly differently, but I guess in an equivalent way because this is just the product with itself.
Yeah.
It's not the product.
Well, it's not exactly the product with itself, but it's
No.
sort of, right? Like,
It's just a way to select the.
yeah.
Here you have this, yeah. Right, so then that's part of this exercise here, which is again probably kind of long to do this, right? But so maybe that's okay. We don't do that, but this summation is going to be the same as that limit. So then they're all equal. That summation is the same as that limit, which is the same as all this, which is all equal to AB. So they're all equal. There's not so much to say. Just had to show that SNN was equal to BA, and then everything's equal.
Yeah, I guess that it could be trivial if you let me think a little bit. Right. So if you define a new matrix, let's say what letter are we not using? Whatever. T? Well, I don't know. If you define a new matrix that is just, for the position ij is basically ai times bj.
Mm-hmm.
I guess then it follows from 2.8.1 that the decays.
Like that's what I was thinking too.
Because like in where? So like in the theorem 2.8.1, in the proof, in the exercise 2.8.4, at some point they say something like, okay, maybe yeah, there. You see, it says for the moment consider m natural to be fixed, and then write as mn that way.
Mm-hmm.
So I guess that's the part where they actually tell you to use it, and they ask you to imitate it just because in there it's not really like a formal result, right? Like
Yeah. Okay. Yeah. Right. So I mean, it would be interesting to go through this, but it's I think a little long, and I think we're pretty much at the end of the session for today, so probably call it there. But yeah, all interesting stuff. Okay, guys. Well, I will wrap it up there for today. So I think that's a good ending place. I think the epilogue is also something interesting to read, which is getting into the next stuff. And so next time we will start talking a little bit about the topology of R, and it's fairly basic topology. So we'll see how much we get through. I mean, some of the exercises probably are interesting, and just to a little bit of a different view of things here, right? So we can maybe try some of this. I'll prepare some questions. Hopefully next time we can try to get through 3.2 and 3.3. Although 3.3 actually probably deserves a lot more discussion for compact sets. So
Yeah, I actually the last part that I read was the beginning of compact sets. I haven't read yet
yeah.
Heine-Borel theorem or whatever.
Yeah, right. Which is of course a really key theorem. So maybe we'll definitely get through all of 3.2 next time, and then we'll start 3.3. But we won't. I don't think we should put it on to have to finish 3.3 because I think it actually does deserve quite a bit of discussion. And then 3.4, 3.5 will go a little faster. 3.5 is just Bayes' theorem, and 3.5 is another one of those kind of like do it yourself kind of things where you go through. The theorems are there, but then they give you a bunch of exercises throughout to kind of go with it, so we can kind of follow that together as well. But anyway, so for next time, 3.2, 3.3 is the main deal. Okay, guys. Well, I'll stop recording. That's my spiel for today. Thanks.